The future of our natural world hinges on a global transition from fossil fuels to renewables like solar and wind. But what happens when the sun doesn't shine or the wind doesn't blow? That's where batteries play a crucial role in storing our energy for when we need it. But have you ever looked at a battery and wondered what's going on in there? The middle part of the battery, called the electrolyte, is like a river, which carries lots of positive and negatively charged particles called ions. Fundamentally, a battery works by storing these ions on one side of the battery and then ferrying them back and forth across the river, charging and discharging the battery. How quickly these ions move through the river is very important for battery performance, and understanding the different pathways that these particles can take through the electrolyte allows us to design new shapes and terrains within our material to optimize this movement. Despite being invented 200 years ago, scientists are still using trial and error to investigate new battery materials, wasting copious amounts of time and money on things that just don't work. But there is a better way, and that's where my thesis is making an impact. I use a computer to create a model of what an electrolyte looks like at an atomic level, zooming into a battery like a microscope, only 1,000 times more. My computer and I will give every atom in my electrolyte material a force field. And when these atoms come close to each other, they bounce off one another, kind of like a massive game of bubble soccer. This allows me to create a movie of how all the atoms in my material move over time. Some rivers may have too many rocks in the way, which prevent our ions from moving through quickly. Others might be too thick, like having a river of honey. And understanding these properties at an atomic level allows us to design better materials from the ground up. I have run hundreds of simulations of many different electrolytes to see which will give us the top speed. And then only the winners of the race need to be tried out in a real-world laboratory, which reduces our chemical waste. With an optimized electrolyte, our batteries will charge faster and hold more energy. My research focuses on finding new materials which avoid the use of flammable and toxic compounds, so that the batteries I make will not only contribute to a more sustainable future, but a safer one. This method of material investigation and the electrolytes I found could transform the battery industry, creating technology that is becoming more and more vital with every day we work towards preserving our environment and achieving net zero carbon emissions.